Okay, so what we're going to do in this part is generate an IV curve for a couple diodes in LT-Spice and see how that compares to what we've been looking at so far in the lecture. So first of all, I'm going to select a diode so I can hit D on the keyboard, or I can grab it off here from the toolbar, and I'm going to place a diode, escape out of that mode. I'll hit R to place a resistor, Control R on the keyboard to rotate it, and then I click to place, escape out of that, and now I'm going to place a component. So I'm going to pull up the component menu with the keyboard shortcut F2, and I'm going to look for a voltage source. So we'll just start typing volt. That pulls up a voltage source. I'll hit OK, and then I will place that too. Okay, so now I need to wire these up. I can use the wire tool, or I can hit F3 on the keyboard, and I will just single click between each place where I want to have a wire connected. And when I'm done with that, I can right click or hit escape on the keyboard to end that mode. And now I need a ground symbol. So I can pull that from there, or I can hit G on the keyboard, and I'll just place that where I want ground to be for that circuit. Okay, so now I have a voltage source called V1, resistor called R1, a diode called D1, and I need to pick a value for this diode. So if I right click on the diode itself, it'll pull up this little menu, and I can hit pick new diode. And let's see here. Normally if these are sorted by part number, you'll see this 1N4148, which is a very common silicon diode up near the top. And we have a lot of those in the lab, so I'll just pick that as our diode for this simulation. Then if I tried to set up the simulation at this point, I'm going to get a couple of errors. And in case you see those pop up, I'm just going to set up the simulation and try to run it without giving values for the resistor or for the voltage source, so you know what that looks like. Okay, so I'm going to do for this a DC sweep. So that means that this voltage source is going to change values. So it's going to start at a low value and then slowly increase in increments throughout the simulation. So I need to know the name of the source, and the name is right here. It's V1. So I'll type that in here. And this is a linear sweep. It has a starting value. We'll start at 0 volts, and we'll stop at, let's say, 15 volts. You can put in a V, or you can just leave it with no units. Either way will work for this. So we're starting at 0 and we're going to 15, so now we need to figure out how many chunks we're progressing in. So I'll say something very small will only increase by 0.01 volt increments. Okay, so now when I hit OK for the simulation, I'm going to get this error because I didn't actually give a value for the resistor. So it says can't find definition of model R. I'll say OK. Missing resistance value. Yep, that's the problem. And then it'll also pop up with this. So in order to get rid of that error, I will have to right click and give this a value, so we can make it a 1 k ohm resistance. And then I can try to simulate this, and I'm going to get another error right here. And this, if you look in the actual error dialog, is saying that there's an unknown parameter V for V1. And that's popping up even though we've said the increments and the start and stop value for the voltage source. The simulation doesn't like it if you don't give some value for this voltage source to start with. So it doesn't matter what it is, because the simulation is going to ignore it and do the DC sweep anyway. But if we just right click on the voltage source to pull up this menu, and we'll just put in something like 0 volts, since that's our start value, and then we try to rerun the simulation again, now it should be fine. Yeah, so no errors, and that means I can now measure my current or voltage or whatever I want to look at for this circuit. Okay, so what we were looking for is trying to create a VI curve or an IV curve for the diode to see how it responds. So I'm going to just measure the voltage here, single click there, and if I single click, LT-Spice will assume that my other reference point is ground, so it's the same thing as clicking and dragging down here to ground. And this is showing the voltage on this horizontal axis here. This is the voltage V1. It's going from 0 volts all the way up to 15 volts. So it's like I'm cranking up the knob on the voltage source basically over a short period of time. And then up here, this is the diode voltage because we're measuring across this diode here. And that starts at 0 volts. And that goes up to somewhere around the knee voltage for a silicon diode, which is like maybe 0.5 volts. You'll start to see a bit of a change, and then it should hold steady somewhere around 0.7 volts. So that's basically what we're starting to see here. Around 0.5 volts, we get this bend in this voltage curve here, and then it's starting to hold steady and it's somewhere around 0.7 volts if we just follow this 700 millivolts across. Okay, so this is basically the curve that we were seeing before. It's just oriented a little bit differently. So I'll just take this into annotation mode real quick. And if you remember, this is the curve that we expected to see. And this basically is that curve. It's just oriented in a different direction because we have a different axis going on here. Okay, so I'll just clear those and get out of annotation mode. Okay, so this is also showing voltage on both axes. And if I looked at current, I could also do that. So when I mouse over this diode, the cursor turns into a little ammeter, and it shows the direction that it thinks current is flowing in with that little red arrow. So it thinks current is flowing down, which would be accurate for this case. And you can see that current is going to start off at 0. And then as our voltage is increasing, we're going to see a sharp increase in the current. And that's because we're going to have 0 current flow below that knee voltage for the diode. But once we surpass that, then we're going to have current flow increasing as we increase the value of that V1 voltage source. Okay, so that's our basic silicon diode in forward bias. So now we could also see what happens in reverse bias. And in reverse bias, we would expect to have 0 current flow or something that's very, very, very small. So I'll just do that real quick here. And I'm going to go select the move tool. And I'm just going to grab this with a single click, hit Control R to rotate it a couple times, place it back in, and now it's in reverse bias. So simulation didn't change, and that's because we have to rerun it every time we make a change to the circuit. So I will just hit this little icon here to run the simulation. And you can see that when we're looking at the diode current, it says ID1, that's the current flowing through the D1 diode. This current is in the nanoamps range. So it's a very, very small current. And it says it's negative because we have a very small reverse current that's flowing opposite in the direction of this little red arrow, which is the direction that LT Spice thinks the current should be flowing in. So it's negative because it's flowing opposite that direction. And it's a very, very small value because there's almost no current that can flow through a diode in reverse bias, which is why we model reverse bias as an open switch. Okay, so now I am going to start to show you what we're going to get into next, and that's going to be Zener and avalanche diodes. So these are a little bit different, and I'm going to replace this diode with a new one. So I'm going to right click, pick new diode, and I can change the filter here by type, and I'm going to look for Zener diodes. Okay, so there's a whole bunch of them. And then up at the top where Zener diodes start, there's this 1N750. So I'm clicking on that, I'm going to hit OK, and our diode type has updated to 1N750. So this is now a Zener diode. And you can also see that the schematic symbol has changed a little bit. So where this used to be just a straight bar across, it's got these little things on the end of it. It kind of looks like a Z for a Zener diode. Okay, so what I'm going to do is rerun this simulation. And this curve has definitely changed. So current is passing, and this is still hooked up in reverse bias. So you wouldn't necessarily expect that. But Zener and avalanche diodes behave differently, and we're going to see how that is. So I'm also going to add this voltage here, and we can see that this knee voltage for this diode is looking like it's somewhere around 5 volts. So even though it's hooked up in reverse bias, once we get to applying about 5 volts to it, we're going to see some current flow through that diode, even though it's hooked up in reverse bias. And that's going to be actually how we expect to use Zener diodes. They're designed to be used in reverse bias. So that's why we also have a different schematic symbol for them, because these are designed to be used in reverse bias, but normal diodes aren't necessarily. Okay, so that's it for this little looking at things in LT-SPICE, see how it simulates, and then we'll start talking about Zener and avalanche diodes.